So here we have to check the boundaries. Okay, means the tangential components and normal components here. So here consider one boundary and consider a closed path. Okay, this is a rectangular closed path A, B, C, D and A. Okay, A, B, C, D, A is the rectangular closed path, and the total height of this path, actually some part is in region 1 and some part is in region 2, right? So when we are considering the upper part, means upper part is region 1 is placed in region 1 and the lower part is placed in region 2, right? So the width of this is delta W, width is delta W, and the height is delta H. Okay, total height is delta H on both sides. Total height is delta H and total width is delta W. Okay, and we have to consider here the electric field intensity component. So the electric field intensity is E bar at this boundary, and here it is having both normal and tangential. Okay, tangential component here, you can see the tangential component is there, and this vertical is your perpendicular is nothing but your normal component. Okay, similarly here there is one more cylinder. Here for we are considering uh, as we are considering the length for the electric field intensity. So for this purpose we have considered here is a closed path, right? And here we are considering one cylinder which is having the differential surface area delta S and the total of this cylinder. Now this cylinder is placed half part of cylinder is in region 1 and half part of cylinder is in region 2. Okay, and total height of the cylinder is delta H. And again we are finding this d bar component, and this d bar is having two components. First is the normal component and second is the tangential component. Okay, tangential and normal component. So all of you understood this figure, boundary conditions समजलंय काय काय? फक्त here it is a closed path. It is this electric field intensity having two components, tangential and normal, and here one cylinder, total height delta H, and this d bar is having again two components, that is tangential and normal. Okay, so here all the explanation is given here again. So here when we are considering this closed path, that is A, B, C, D, A, right? This is the closed path. So half part of this is in region 1, that is in dielectric 1, and the remaining half part is in dielectric 2 medium, right? So if the total height is delta H, if the total height is delta H, I can say that here delta in this dielectric 1, the half part is there, right? That is equal to delta H divided by 2. And in region 2, that is delta H upon 2 part is there, right? Na? Right? All of you getting? समजतंय का? प्राजक्ता समजतंय का? Yes or no? Okay. So now here we are applying this for the for this clothes. Okay. We are applying this for the closed loop, that is A, B, C, D, A. Now when we are considering that a closed loop is there, so the closed line integral of E bar dot dl bar is equal to 0. E bar dot dl bar is equal to 0. So we have to consider this for all the lines, okay, of this loop. That is, it is equal to, if we want to find the line integral of the closed loop of this E bar dot dl bar, it is nothing but the addition of the line integral of from A to B of E bar dot dl bar plus integration from B to C of E bar dot dl bar plus C to D of E bar dot dl bar plus D to A of E bar dot dl bar. Okay. So here the sum is given and it is equal to 0. It is equal to 0. Then now E1 bar and E2 bar we have to consider. So this E1 bar is nothing but the electric field intensity in region 1. Okay, E1 bar is the electric field intensity in region 1, that is in upper part, and this E2 bar is the electric field intensity in region 2. So this E1 means electric field intensity is having two components. One is the tangential components and second is the normal component, right? So this E1 bar is equal to E1 T bar plus E1 N bar. Okay. Similarly, for region 2, E2 bar is equal to E2T bar plus E2N bar. Okay. So, these are the electric field intensities in region 1 and in region 2. Okay. Now, this mod of E bar 1T, here we are taking just, here you can see, we are taking just the magnitude of this. Okay, this is the electric field intensity in region 1 and it is the tangential component. Okay, and what is this E bar 1n? This E bar 1n is the electric field intensity in region 1 and this is the normal component. Okay, this is the normal component. Okay, so similarly, this is tangential component. Similarly, mod of E bar 1n is nothing but E1n. Then mod of E bar 2t is E tan 2 and mod of E bar 2n is equal to E2n. Okay. Now at boundary, this delta H tends to 0. Right. This delta H tends to 0 at the boundary. So when this delta H will become 0, when delta H will become 0, so see here, at this boundary, okay, at the boundary, this delta H is equal to 0, right? Total height is delta H, but this delta H becomes 0 at the boundary. Then just tell me which sides become 0. Which sides become 0 when this delta H is equal to 0? Yes, anyone? Which sides will become 0 if delta H tends to 0? Hello? So, which side will become 0? Which sides will become 0 if delta H tends to 0? So, when this delta H tends to 0, that time the sides BC and DA, okay, the sides BC and DA will become 0 here. Okay. So, here B to C of E bar dot DL bar and D to A of E bar dot DL bar, it becomes 0 when this delta H will become 0. Now, hello. So now, for medium 1, this A to B is placed in medium 1, right? In medium 1, this A to B part is there, and in medium 2, C to D part is there. Ha. Hello. Just wait for 1 minute only. Hello. So sorry. Okay. Now, uh, here, just a minute. So here, when this is becoming 0, now A to B is, we can say that this is the tangential component, right? Because it is horizontal. Horizontal means it is simply a tangential component, and normal is nothing but the perpendicular component, right? So, integration from A to B of this E bar dot DL bar is equal to E tan 1. Okay, it is equal to E tan 1 integration from A to B of DL bar. Okay, A to B of DL bar. And it is equal to E tan 1 into delta W. Now, how it is delta W? So, here now for A to B, you can see here for path A to B, okay, for path A to B. A to B is the tangential component here. It is the tangential component, and DL is the differential length of that path, and it is equal to delta W, right? It is equal to delta W. That's why this integration of for path A to B of E bar dot DL bar is equal to E tan 1 integration from A to B of DL bar, and this DL bar is nothing but delta W. DL bar is nothing but delta W here. Okay, now Similarly, we have to consider the next path, which is in the region 2, right? Now in region 2, see here, in this region 2, the path is C to D, right? Path is C to D, and it is in region 2. Again, the differential length is delta W here. The differential length is delta W. Just see here now. Now, for path C to D, this path C to D is in medium 2. Integration from C to D of E bar dot DL bar is equal to minus E tan 2 into delta W. Okay. Now, why it is minus? This minus sign indicates that there is opposite direction, right? Minus sign indicates that this is the opposite direction. Therefore, now this close, therefore, this line integral for path A to B of E bar dot DL bar plus C to D of E bar dot DL bar is equal to, for path A to B, it is E tan 1 into delta W, and for path C to D, it is minus E tan 2 into delta W, and it is equal to 0. It is equal to 0. So we can say that if we separate this delta W get cancelled, and we get E tan 1 minus E tan 2 is equal to 0, means E tan 1 is equal to E tan 2. Okay. So up to this point, any doubt? Up to this point, any doubt? समजतंय का? Yes or no? रेणुका? Yes, anyone? समजतंय का? श्रद्धा? वर्षा? Hello? Harshvardhan? Not a single reply. Are you present in lecture or not? Harshvardhan?
हेलो. यस मैम.
Yes. समजतंय का?
हाँ मैम.
Okay. Now, here we obtain the equations for E bar only. We find the tangential component. We find here tangential component, right? Of this E of electric field intensity. Similarly, we can find tangential component of D also, that is electric flux density. Okay. Now, how to find this? So, here, so what is the relation between D bar and E bar? D bar is equal to what is relation between D bar and E bar? Yes, you have just given the ISC and this question was asked in ISC also. Yes, relation between D bar and E bar. Okay. So this D bar is equal to epsilon E bar. So we have to find here the tangential component. So D tan 1 is equal to epsilon 1 tan 1, and D tan 2 is equal to epsilon 2 E tan 2. Okay. So from this only we can find the relationship. So D tan 1 divided by epsilon 1 is equal to E tan 1. And what is the relation? E tan 1 is equal to E tan 2. So we have to write this in terms of the E tan 1 is equal to E tan 2. So E tan 1 is equal to D tan 1 divided by epsilon 1, and E tan 2 is equal to d tan 2 divided by epsilon 2, right? So these two are also equal, but how they are related? They are related with permittivity. Remember, when you are considering the electric field intensity, the tangential components are same. That is E tan 1 is equal to E tan 2. But if you are considering the electric flux density, that time, this it is related by the permittivity. Okay, so this d tan 1 divided by epsilon 1 is equal to d tan 2 divided by epsilon 2. So d tan 1 divided by d tan 2 is equal to epsilon 1 divided by epsilon 2. And this is the general, okay, permittivity. So this permittivity can be written as epsilon is equal to epsilon 0 into epsilon r. Okay. So epsilon 0 in this is for epsilon 1, it is epsilon 0 into epsilon r1, and for epsilon 2 it is epsilon 0 into epsilon r2. So epsilon 0 get cancelled here, and the remaining terms are only epsilon r1 and epsilon r2. Okay, so I hope everybody understood the tangential components of both electric field intensity and the electric flux density. Okay, in tomorrow's lecture we'll see the normal components. Okay, so now we'll stop here. So you are having the training. Okay, no problem. So thank you all. I'm ending lecture now. Thank you.